All right, let's dive into the hidden world of displacement reactions. We're talking about a chemical power struggle, where elements are constantly competing, pushing, and shoving each other around. So how does this invisible battle actually work?
It might sound a little out there, but this chemical fight is literally the reason we have the technology we use every single day. In fact, the outcome of these tiny battles is what makes the very device you're watching this on possible.
So to really get a handle on what's happening at the atomic level, we're going to start with a powerful analogy. Let's think of this whole thing as a power struggle, kind of like a chemical bully scenario where some elements are just, well, more aggressive than others.
Okay, so here's the official definition for you. A displacement reaction is when a more reactive element straight up pushes out a less reactive element from its compound. Think of it like a chemical substitution, where one element just muscles its way in and takes another one's spot. And this really paints a picture, doesn't it? Imagine two metals are fighting over a non-metal partner. The one that's more reactive, it wins the fight, grabs a partner, and leaves the other poor element all by itself.
Now, that fight analogy is super helpful, but we gotta be a little more precise with our language. In chemistry, strong usually means something else, like physical durability. The correct term for this chemical power is reactivity. It's all about how badly an element wants to form new bonds.
So if this is a competition, how do we know who's going to win? Is it just random? No way. Chemistry has a totally predictable rulebook for this, and it's called the Reactivity series.
This series is basically the leaderboard. It ranks elements from most reactive at the top to least reactive at the bottom. But wait, check out the surprise guest hanging out in the middle, carbon. Now, as a non-metal, it might seem a little out of place, but its position right above metals like iron is the secret sauce for huge industrial processes. We'll get to that in just a bit.
And here it is, the golden rule. It's so simple, it's beautiful. An element can only push out another element that is below it on this list. The reverse can never happen. An element lower on the list just doesn't have the chemical oomph to kick out one above it.
Okay, theory is one thing, but now let's actually see a reaction in action. Nothing makes this clearer than watching the chemical swap happen right before your eyes.
Here's a classic experiment from the lab. If we look back at our reactivity series, we know that magnesium is way above copper. So it's no surprise that when magnesium meets copper sulfate, it's going to shove that copper right out of its compound.
And here's that same reaction, just written in the language of chemistry, using the symbols for each element. You can see it clear as day. The magnesium, Mg, has totally swapped places with the copper, Cu.
But what would you actually see if you were standing right there in the lab? Well, you'd see some pretty dramatic changes. The blue solution, which gets its color from that copper compound, would slowly turn clear. And at the same time, you'd see this brownish solid, which is pure copper, start to form as the silver magnesium strip just dissolves away. It's a visible chemical switch.
Now that chemical switch we just saw, it's not just some cool trick for a chemistry lab. If you scale this up, and I mean way up, that exact same principle is how we get pure metals from rocks to build our entire world. This is where carbon's spot on that reactivity list becomes a multi-billion-dollar advantage. See, because it's more reactive than iron, we can use super cheap, plentiful carbon to basically steal the oxygen away from iron ore. You just crush the ore, mix it with carbon, blast with heat, and bam! The carbon bully displaces the iron, leaving you with the pure metal.
And that brings us full circle, right back to the phone in your pocket. This same idea works for other metals too. We can take cheap scrap iron, which is more reactive than copper, and use it to pull valuable copper out of mining waste. That simple chemical switch is a crucial step in getting the copper we need for all the wiring inside our electronics.
All right, so just when you think you've got this whole thing figured out, chemistry throws us a little curveball. This powerful rule, this whole reactivity pecking order, it doesn't just apply to metals.
Say hello to the halogens. They're a family of nonmetals. And guess what? They play by the exact same rules. As you can see, chlorine is the champ here, the most reactive bully on the block. And way down the list, you've got the much less reactive iodine. They have their own little hierarchy.
So you can probably guess what happens, right? If you bubble that superreactive chlorine gas through a solution that has bromide in it, the chlorine just effortlessly kicks the bromine out and takes its place with sodium. It's the exact same principle we saw with the metals. That pecking order holds true.
But what if we try to flip this script? What happens if we add the less reactive bromine to a solution with chlorine in it? You guessed it? Absolutely nothing. It is a total non-event. Bromine just isn't reactive enough to displace chlorine, which proves that this chemical hierarchy is a fixed, predictable rule you can count on.
So, what's the big takeaway from all of this? Well, from yanking iron out of a rock to getting the copper needed for a phone, it all boils down to the same simple idea. There is a predictable chemical pecking order, and the more reactive element is always going to come out on top.
And that leaves us with one last thought to chew on. We've just seen a clear, invisible hierarchy that literally dictates how matter itself behaves. It really makes you wonder, what other invisible pecking orders and hidden rule books are out there shaping the world all around us?